Today we will have a short excursion at the mega project called NICA, which is being created on the territory of the Joint Institute for Nuclear Research in the city of Dubna, near Moscow. In my lecture, I will briefly discuss the institute, mega project NICA, collider, where we are now, and I will show you some interesting footage. The Joint Institute for Nuclear Research is an international and intergovernmental organization created in 1956. At the moment, 24 countries are participating in projects taking place in the institute, with 18 countries as full members and 6 countries as associated members. The only difference between full membership and associated membership is that both members participate in experiments and scientific activities, but full members have the right to make decisions about institute management. The institute is extensive by all standards, with the infrastructure occupying almost half of the city. The institute has 7 laboratories and university center. Laboratories are fairly large subdivisions with their own basic facilities, reactors, cyclotrons, detectors, and other accelerators and facilities. What is this project? This is the construction of a heavy ion collider with 2 accelerating rings, 2 ion sources and 3 detectors located at the point of interaction of our accelerated beams. The mega project will carry out both fundamental and applied research. I will briefly tell you about the history of the project. In 2011, this project was presented to the government of Russian Federation, where it was approved as the part of one of mega science class projects under the development in our country. In total, 28 projects were proposed and only 6 were selected. In 2013, the project was approved by technical experts. In 2014, the preparation of technical documentation began and the construction itself began at the end of 2015. We did not have to build the entire infrastructure from scratch, because the main building for the accelerator complex, as well as the ion acceleration ring, referred as the nucleotron, was already built many years ago and has been adapted to the new tasks. By the way, in 1957, the first resonant cyclic accelerator, known to many as the synchrotron, was put into operation in this building, and we are in the same room right now. This accelerator actually propelled us into the international arena in the field of high-energy physics, with its ability to accelerate protons to a maximum energy of 10 gigaelectron-volts at that time. The launch of synchrotron caused widespread acclaim in the world and was recognized as an outstanding achievement of science. Also next to this building is another building used for experimentation, which was also repurposed and in which we locate our fixed target experiment called BMN, Baryonic Matter at Nucleotron. What concerns the new buildings, it was only necessary to construct the collider ring building, a new compressor station to supply the accelerator with helium, and also to adapt the existing premises for the magnet factory and detector part assembly workshops. At present, the construction of the collider ring is being completed. The collider magnets are being prepared, and the heart of the experiment, which is the MPD detector, is being assembled. It is a multi-purpose detector in which collisions will occur. 2 years from now, the first run is planned to take place, the so-called first run of the beams throughout the entire complex, which in fact will be the start of the first experiments. After that, work at the collider will begin and will continue until the facility has completed its tasks, which is predicted to take about 20 or 30 years, since the accelerator will undergo various upgrades and operate in different configurations. Let's take a look at a classic collider diagram. It all starts with the source of our particles, protons, electrons or ions. From the source, the beam enters the linear accelerator, where after gaining a sufficient amount of energy, it goes into the accelerating ring or booster. and then it enters the collider rings, where a collision occurs at a certain point. The detector is located at this specific collision point. Now let's look at each node individually. The source is very first node that prepares the beam of particles we need to accelerate: electrons, protons or ions. At our complex we have two sources, one consisting of light ions ranging from hydrogen to magnesium, and the second made up for heavy ions. At the start, gold will be used as a heavy ion, and in our source we will remove 31 electrons from the gold atoms. On a heavy ion linear accelerator, we call it by its abbreviation HILAC, meaning heavy ion linear accelerator. This is just over 3 MeV per nucleon. But we need to increase the speed of the accelerated beam almost 2000 times faster. In order to avoid building a very long linear collider or linear accelerator, our first director, Vladimir Iosifovich Wexler, invented the synchrotron. This is what the first accelerating ring booster looks like. Intrinsically, it is located inside the old synchrotron. Since its magnet is very heavy, instead of dismantling it, it was decided to assemble a booster ring inside the synchrotron. On the one hand, we preserved it as a monument, and on the other hand, it serves well as a biological shield. So we have made the most of what has been built over the past 60 years. The main tasks of the booster are the accumulation of ions from the linear accelerator, the subsequent final stripping of electrons, that is, in the booster we already get pure gold ions without electrons, and acceleration about 600 MeV. After that, the beams move into the second ring, the nucleotron, which is the same one that was built 30 years ago and which is located directly under the booster. In the nucleotron, we accelerate the ions to an energy level of 5 GeV per nucleon, after which the beams move into the collider ring. Next, with the help of a bending magnet, we fill up two collider rings with beams. The collider ring provides the accumulation of beams and the formation of short bunches. At this stage, no further acceleration takes place, since the goal is only to maintain the level of energy with which the ions came from the nucleotron. At the time of this recording, construction of the building that will house the collider ring is coming to an end. All that remains to be done is the interior decorations, as well as installing the necessary equipment. At the same time, the magnet factory is already producing new magnets that will be installed in the collider ring. We have now discussed the main parts of our collider. Of course, there is a lot more that I could tell you if we had more time. For example, we also have a cryogenic station here, a power station for the collider, and a data center that will collect all this data. Perhaps I will tell you more about this in another lecture.
Such a complex cannot do without applied research. Therefore, the project is referred to as a mega project, since it contains not only physical tasks but also tasks aimed at improving our quality of life. Today, it's difficult to imagine medical, chemical or biological research without nuclear physics. After all, it's nuclear physics that allows us to study and observe the smallest bricks of matter, and thus, having analyzed its nature, this knowledge can be used in many areas of science. In medicine, the focus is primarily radiation therapy, which is becoming more and more effective, while the latest tools help in the fight in oncology, especially in cases where surgery is not possible. Further experiments using a medical beam are planned to be carried at our complex. We can try to accelerate not only recently proven protons but also other particles. In the field of biology, our institute is already conducting experiments to study the effects of radiation on other organisms in the laboratory of radiation biology, and experiments in this area will be carried out at our complex. And in the field of material science, we will be able to use radiation of our complex to test new materials. For example, in the lining of spaceships, which will allow us to improve protection against direct cosmic radiation, and in the future send astronauts on long-term journeys, as we have seen in movies. New experiments are also planned in the field of metallurgy, chemical production, heavy engineering, and other industries. The NICA complex will be open for new research concepts.
This project will be in operation for several decades, so we invite everyone to take part in it, not necessarily only physicists, but also biologists and doctors. This is a very interesting application program, so maybe multiple generations will be able to participate in this. Nevertheless, thank you for your attention. I hope that you found it interesting. Goodbye.